Calculating standard deviation comes in two flavors. This formula on the left shows calculating standard deviation on every single element of a whole population. And here, this formula shows calculating it when you only have a fraction of the population, you only have a sample more or less well selected from a whole population. Now, there are some differences. You can see different letters are used in the two formulas, but the main difference is this division that I highlighted here. In this one, if your whole population is 30 elements, you divide by 30. And here, if your whole sample is 30, you throw away one of the samples and you divide by 29. In this video, I'm going to be focusing on why do you throw away one of the precious few samples that you have, and what difference does it make when you divide a number or a square of a number by, say, 29 instead of dividing the same square of a number by 30. Now, obviously, if you have a standard deviation practice problem in front of you, you can just try it either which way. Once you arrive to a square of a number, you just divide by, say, 30 if that's your sample, if that's your population size, and divide by 29, and just see what happens, how the standard deviation changes. This difference in division is known as Basil'S correction. So the sample is to be corrected, and textbooks tell everybody that the sample is corrected to boost its numbers up in simple terms. So in this video, I'm going to show you a systematic approach to what difference does it make when you're dividing by n-1 instead of n. So Basil'S correction is not just the n-1, it can be written in a fraction format. So if this number is 30, then you divide by 30 over 29, or 1000 over 999. You get the idea. So this is the factor that's built into this formula. So on the next spreadsheet here, very simply, I have numbers 1 to 100, and I have one less than a number, 0 to 99. So obviously, if you have 5 here, you have one less here, 4. If you have 10 here, you have 9 here, very simply. So all the way down to 100, at which point here I just switched to 1000. So if you have 1000 here, 999 is here. So all the way down to 100,000 there. Let me just put a 1000 separator there and get rid of the decimal digits there. So now they're formatted the same way. Now, in this column here, very simply, I'm just going to put in Basil'S correction and divide this numerator with this denominator, just like it is represented here. So without this correction, it would be 30 over 30, or 1000 over 1000, and those numbers all equal to 1 in terms of fractions. So I think it's fairly obvious that these are whole number fractions. 5 over 5, or 1 million over 1 million, they all equal 1. These fractions, however, will not equal 1. So 0 here got replaced by a horizontal dash by Excel. So I'm not going to put anything here, because dividing 1 by a 0 is going to not work in Excel either. So the formula very simply is this number divided by that number, and in this case 2 divided by 1, or 2 over 1, is 2. I can just copy the formula down like so. 3 divided by 2 is 1.5. So you can see right away, obviously, that whereas 2 over 2 would be 1, now it's not 1, it's been increased to 2. 4 over 4 is 1, and without Basil'S correction, the standard deviation is not modified. 4 over 4 is just 1, but 4 over 3 is more than 1. It's 1 1/3. I can keep copying the formula down. So you can see that the standard deviation on the sample size is boosted here by, say, this is 33% more than 100%, this is 25% more than 100%, 20%, 16%, 14%, I'm just looking at the decimal number, 12.5% more than 1 or 100%. You can see that especially when the sample size is very low, say under 10, this formula here, the sample variant or sample flavor of standard deviation, gets boosted by 10%, 11%, 12.5%, 14.2%, 16.6%, whatever you can see. So 30%, and this might seem unfair. Why are we giving a serious boost to sample only standard deviation calculation? If I simply copy down the formula, you'll see that the boost here disappears by the time basically to 0. By the time we get to 50 or so, it's down to 2%. If we just continue this pattern, by the time we get to either a population size or a sample size of 100, the boost to the little guy, where you only have a sample of the whole population, it's only a 1% difference. And if the pattern continues, if I copy it all the way down to 100,000, I have 1, 2, 3, 4, 5 decimal places, so it is just the tiniest fraction of a percent how much difference this makes, whether you divide by 100,000 or you divide by 99,999. It only makes a tiny little difference at this magnitude. So you can see it's really more than 1 only for the first, say, 50 or so elements, or the first 100. Now, I'm not going to tell you how significant this 1% is or should be in your line of work, in your research. 1% can mean millions of people if you're looking into efficiency of vaccination. But as far as math goes, relatively, 1% is just a small number. So again, I'm not discussing how significant that small number is, but this is how the math works. This correction here works on even if you have to divide a square of a number. Okay, so in both of these formulas, you're not just dividing 30 by 29 or 1000 by 999. However, this fact that this is a square of a number doesn't make a difference. Let me show you here. Very simply, I'm going to insert here a blank column here, and I'm going to make here the square, capital, the square of these numbers here. So simply the formula will be this number multiplied by itself. Of course, 1 by 1 is 1, 2 by 2 is 4, so the formula works. 10 by 10 is 100. Nice, so there's the square of the same number. Let's pull it down to 100,000. There. Those are the squares of there. Those are the squares of n. And so the division, one more column is needed here. So we're dividing by n, so I'm going to put here n squared divided by n. So the formula is going to look like n squared in that cell is going to be divided by this number there, and in the case of 1 it's still 1, and of course this makes sense that we're back to 2n that we started with, because we are with this division n squared divided by n, we're just getting back the same number that we started with. We are unsquaring a number, so here all the numbers will be the same as in the column n, and the first column here, column A. Alright, so this is how it looks like when a square of a number is divided by a number. So it's essentially the same as the number itself. So here, this, whether it's the sum or what, a sum of differences, it doesn't make any kind of difference. It's this whole thing is just one number after adding everything that's being squared. And here is the same number that's being squared, but divided by one less than a number. So I'm gonna make another column here, where actually I will not. I'm gonna make another column. I'm just gonna write it here. So it's gonna be n squared, and it will be divided by n minus 1. So that's what I'm going to put here on the formula version. So n squared, this number will be divided by n minus 1, which is in this column there. So what number do we get? We get that number. Let's check it. Yeah, 4 divided by 1. Yeah, that's 4. And if I copy it down, it should make some sense. Okay, it's looking like this. So this number needs to be compared to this number. So instead of square of a number divided by the number itself, instead of that, the square of a number here is divided by one less than the number. So these numbers here in column F will be higher than these ones here in column C. So instead of 2, we have 4. And this is Basil'S correction here. Maybe an apostrophe there would be nice. Basil'S correction. And Basil'S correction here says so that this is twice this fraction here. Say I think I started with 30 over 30 or 30 over 29, whatever, increases the fraction, gives us fractions greater than 1, and here this greater than 1 is 2 or 1.5 or 1 1/3 and 25% more than 1, 20% more than 1. So if you look at the numbers this way, here is 3 and here is 4.5, and 4.5 is 1.5 times more than 3, and 4 is 2 times more than 2. I hope this makes sense. And 7.2 is 1.2 times more than 6. So Basil'S correction here, even though it looks like it's in this format here, it still works as it should. This is how math works. But this is just stating Basil'S correction here in a simple fractional format. So if you do the calculation properly, Basil'S correction will be embedded in it, and it shows up. Basil'S correction is a factor, and it shows up in the result here. So if I just copy these all the way down there, what you see here in the numbers, of course, everywhere, is that these numbers in column F again are higher than column C. So we have here 17 and a bit instead of 16. And if we look at the patterns again, after 50 the differences will be tiny. So here we have 52 if instead of 51 when we have sorry, that's not 50, when we have 51 elements in a set. Let's go down to 100. So we have 101, again 1% more than 100. If we have 100 elements in the whole population, or 100 pieces of sample that represent a population. So it's just a 1% difference, kind of tiny. And if we go down to 100,000, here we have 100,001 instead of exactly 100,000. So the differences are getting smaller and smaller. Now I want to point out one more thing, that this is a factor, but we need to take a square root of this factor, so we're not done. So Basil'S correction is a factor in a fractional format, but it's gonna change one last time. So I'm gonna put a column here. So let's take the square root of SQRT bracket of this number here. Close the bracket, and of course it's gonna be 1 there, but the square root of 2 is, it's just some, there we go, some more decimal places. How about 6 decimal numbers? So the square root of 2 is 1.4, square root of 3 is 1.7. Nice, so it's working. Let's go down to 100,000 here quick. There. So with the square root, I'm just gonna write square root here, SQRT of column C. Okay, so this is the square root of column C. So this is the actual finished standard deviation. So the final calculation here, the final result for the whole population. If you have here a say 10 elements in the set, your standard deviation will be 3.16. Now we need to do the same over here. We need the standard deviation of the SQRT on column G there, and maybe make these consistently blue, except this one, which is Basil'S correction. And of course this page came up, you can read about on Wikipedia about Mr. Basil and how this correction came about, and you can read about it in complicated words or whatever. You can see some calculations, but none of them are Excel, and none of them are really visual to explain what difference does it make. And of course you can read about Friedrich Basil and when he lived and whatever. You can read everything about a lot of things. So let's finish this calculation here. The square root of G, column G here, SQRT bracket, not that one, this one, just G3, no, G3 there. Let's check it, make sure it's working fine. Yep, it's working fine. All right, let's finish it all the way down to 100,000. There. And let's go up. So let's see, this is the final standard deviation. So here we have a standard deviation of 2 instead of 1.2, sorry, instead of 1.4 we have a standard deviation of 2.5 instead of 2.2, and you can see that these numbers are quite different, but again the same pattern will continue. It's getting just about the same. You have 5.2 on that side and you have 5.1. We'll call it 5.1, okay, by the time I get down to element 26. And if I get down to say line 100, you can see that we have here standard deviation of 10 and we have here 10.05. So initially, I know I said the Basil's formula only makes a 1%, sorry, a 1% difference there, but once that 1% is square rooted, it's even less than that. So that's why really under 50 here is 7.14, 7.07. if you have less than 50 samples or less than 50 elements to a set that make the whole population, the Basil'S correction is really not making much of a difference. If we go down all the way to 100,000, this is 316.229, this is 316.22. So the first two decimal places are the same. Again, I'm not arguing about scientific accuracy, and I'm just showing you how math works and how Basil'S correction works. And it does. What it does ultimately, it boosts the standard deviation numbers up, especially if you have less than 50 elements to the sample or elements to the set to work with. And this adjustment or this boost is fairly tiny after 50. So that's how much difference it makes, and that's how it works. Thank you very much for watching.